Hello, physics students. So I'm still very excited about yesterday's video where we learned a very important rule about how our universe operates. And that's that under the right conditions, a magnetic field can produce a voltage. Today, in this video, we're going to learn something that I find even more profound, even more beautiful. Another rule about our very ancient universe. And that's that under the right conditions, a magnetic field could create an electric field. So we have electricity, we have magnetism coming together in electromagnetism. So that's what's coming today. Very excited. To demonstrate the principle, what I have here is, well, what I would say an ancient coil that I got out of the storeroom. Maybe not as ancient as the universe, but it's very old. And like I said, it will demonstrate that principle that I just talked about, how magnetic field could generate electric field. So what I'm going to do is reconfigure the camera so you could have a closer, better view. So what I have here is a solenoid on a stand. And inside the solenoid, I've got some iron to magnify the magnetic effects. Now, right now, there's no current in the solenoid, so there's no magnetic field generated by the solenoid. What I'm going to do, though, is I'm going to turn on this power supply and put current into the solenoid. But I want to remind you that this is a DC power supply. That means the current is steady. When I put it up, I'll put it up to, say, around, wait a minute, a wire came out. I'll put it up to around 4 amps. And so it's a constant 4 amps, therefore a constant magnetic field. And we could see evidence of that magnetic field by, again, this iron bar now attracted to the solenoid so strongly that I could lift up this entire heavy solenoid. Now, I'm going to see if that generates a current. To see evidence of that current, I've got a coil here connected to a very simple light bulb. Now the coil, as you could see, is just a copper wire spiraled around and around. And the reason why it goes around multiple times is to magnify the induction effects, to increase the net voltage when that I'm inducing in this coil. So I've got magnetic field, I put a coil in with an area, and we get no light coming on. And you should know why the light bulb didn't come on. Because from the first video in this topic, we know that there's a lot of magnetic field, as we saw. There's an area to the coil, and the magnetic field is going through that area, so the theta here is 0, so we have flux. But the problem is it's steady. And Faraday's law that we learned in yesterday's video is that the voltage in the coil is equal to the rate of change. You have to have a changing flux for this bulb to light for there to be a voltage and therefore current. So DC, not adequate. So I'll shut this off and get this out of the way. Now, I don't know if you noticed, but this has a plug that can go into an outlet. So I'm going to put a disclaimer here. If you have a coil like this at home, which you probably don't, do not try this at home, because when I plug this in, the electricity will be delivered to these posts. These will be live with no protection. I plug this in, I go like this, I get electrocuted. So there's no safety mechanism to this coil. So I'm going to plug this in now. And the thing about the wall outlet is it oscillates. So the current now is oscillating back and forth 60 times per second. And that means the magnetic field coming out of the top of the solenoid is going up and down, oscillating 60 times per second. Now I will have a changing flux because I'll have a changing magnetic field. And when I put the bulb on, you could see that it does indeed light up. The oscillating magnetic field creates that oscillating current in this coil, which lights the light bulb up. But here's the thing. Why does this demonstrate that the magnetic field changing through here creates an electric field? Because think about this coil. The electrons have to be propelled along this coil, first one way, then the other, which means they have to have a force on them, an EMF, an electromotive force. How is it possible for an electron to feel a force along the wire? As we know from electrostatics, a charge experiences a force only if there's an electric field. So as this a given electron is propelled one way, there must be an electric field along this wire going this way. And then when the electron's propelled the other way, there must be an electric field going that way. So the changing magnetic field through the coil creates an electric field along this path. That's the beautiful principle of today. So let me reconfigure the camera so that we could summarize on the board. So today's notes are titled Induction and Electric Field. Now here's the main equation that says what I talked about in the demonstration. And you may recognize Faraday's law within this equation. The EMF, the electromotive force, the voltage produced in a loop is equal to the time rate of change of the magnetic field with a minus sign in there. But today, what we do is we just think about what voltage means around a loop. When there's a voltage around the loop propelling a current, there must be an electric field, a force, an electromotive force along that loop that the magnetic flux goes through. And so that's what we're writing here. The EDS, that's one definition of voltage. The electric field along a path is what propels electrons and gives them a thrust. Voltage, electric field that runs along the path. That's why we need a dot product. Not a path like this, an electric field like that. No, the electric field has to be aligned with the path, the dot product. That's what that's there for, to propel the electrons along that path. And we're going around our closed wire loop. Okay, so there's the expression. But here's the extra concept. A changing magnetic field produces an electric field that is perpendicular to the magnetic field. This changes within the flux. A changing magnetic field makes an electric field. Electromagnetism together, both parts of one phenomenon, electromagnetism. So let me create a pause to allow you a chance to copy these notes down. Now, what we're going to do is an example, one calculation of how we can apply this concept to find the electric field that inside and outside of a solenoid with a changing magnetic field. So imagine I have a solenoid here that I pass current through, and so I put current in one post and another, and so the current spirals around here, producing an electric field, either coming out of the solenoid this way or going into the solenoid, doesn't matter. And so inside the solenoid, we've got magnetic field, and if the solenoid's very long, like an ideal solenoid, there's no magnetic field out here, only inside this solenoid. We're going to find the electric field that's produced when the magnetic field changes inside the solenoid, the electric field, and the electric field outside the solenoid. So two different places, inside and outside. So that's the example. We got a long solenoid, radius capital R, with a changing magnetic field in it. We're going to determine the electric field everywhere. We're going to start with inside the solenoid, radius R, we're in here, and we want to know the electric field when maybe the B increases, the magnetic field increases. So what we do is we imagine that we put a wire here. I'll draw it really light because I don't want to emphasize the wire. As the B is increasing, the electric field must be produced such that if this were a wire, the current in that wire would produce a magnetic field that opposes this change. That's Lenz's law. So that's what I'm going to do first, is figure out the direction of the electric field. My choices are that it goes in the clockwise direction or the counterclockwise direction. What I'm going to do is I'm going to make a pause and give you a chance to figure it out first. So go ahead and see if you could figure out which way the electric field goes. Here it is. So with this B increasing, the induced magnetic field has to oppose this increase. In other words, it's got to go into the board to oppose out of the board increasing. Then, if this were a wire loop, we would use this right-hand rule to figure out the direction of the current in this loop. In order to make B induced into the board, I got to have current going this way in the clockwise direction, which means that the electric field goes in the clockwise direction. So there is the electric field generated all around this loop. Well, I guess that's enough of them. I've got electric field going that way. Why? Because the magnetic field increased because of this relationship. Now what I'm going to do is calculate what that magnetic field is based on the time rate of change of the magnetic field. So I'm just going to use this principle over here. And so first I need to find the flux so that I could take the derivative of the flux. That's the name of the game with this Faraday's law. So BA cos theta. Now the magnetic field at a particular time is B, but the area of this loop is the area of a circle. It's some radius r less than capital R, so its area is pi r squared, and the angle between the magnetic field and the area vector is 0 degrees. That makes a very simple flux expression, B times pi r squared. Let me create a pause to allow you to copy these notes down. Let's move on. Okay, so as I said, the voltage around that path, which is equal to the integral of E ds, will be equal to the time rate of change of the magnetic flux. But this, since from symmetry arguments I can conclude that the electric field is a constant all along this path, and it lies along this path. So this is kind of like Ampere's law. When we integrated B ds around a circle, we could just say that this is E ds around a circle. So the integral will just be E times the circumference ds integrated around a circle, or 2 pi little r, because, again, our radius of our circle is little r, not capital R. And then on this side, I'll plug in the expression for the magnetic flux, B pi r squared. Well, pi is a constant, so is the radius of our loop that we imagined going inside of our solenoid. So the only thing that's changing is the magnetic field. So I can write E times 2 pi r. And maybe what I'll do is I'll ignore the minus sign because I already figured out the direction of the electric field. And so I have pi r squared dB dt. The pi's go away. One of the radii goes away. And I could divide both sides by 2, and I get the expression for the electric field inside the solenoid. All right, let me create a pause to give you a chance to copy those notes down. All right, what does that formula say? It says that at the center of the solenoid, radius 0, no matter how much you change the magnetic field, there's no electric field at the center. But what it says is the further you go out, the more electric field you have, and the faster you change the magnetic field. Change it gradually, you'll get a little bit of electric field. Really crank that magnetic field, get a big derivative so it changes very rapidly, and you got a lot of electric field. So that's what affects the electric field inside the solenoid. Now, what about outside the solenoid for R greater than capital R? Out here, is there an electric field? And what is its magnitude if there is? So let me make some room. So here is our solenoid, radius R. We've got a B. You know what? Maybe I need it a little bit bigger. I could see already I'm going to run into trouble. B like this, capital R. And we want to know the electric field out here. Is there one, first of all? And if there is, what is its magnitude? So what we do is we imagine a loop. Imagine we put a wire here. First thing, is there a voltage induced? And if so, what direction? The answer is yes, there is a voltage if B is increasing. Because we have more and more magnetic field coming out the board. And so B induced tries to keep that from increasing. As this is increasing, B induced goes into the board. And so it's like before. We've got, in order to have magnetic field, if this were a wire, into the board, we would need current going, again, in the clockwise direction. So we have current, in other words, but we don't have current because there's no wire, but we do still have the electric field in space that's going around this way. So yes, there is, but now we want the magnitude, so we will use essentially Faraday's law again, but expanding out what voltage really means. It's the electric field along a path. And maybe what I'll do is just find the magnitude. So I will just go like this and say the magnitude of the voltage. This is like Ampere's law again. The electric field is a constant around a circle, so it comes out of the integral. We're just integrating ds around a circle. In other words, we're integrating ds around a circle, which gives us 2 pi r. And then over here, the flux this time is B, A, but the area is not the area of our entire circle out here, of our entire loop. The magnetic field, the flux is only inside of our solenoid. So before we had pi times little r squared, now we only have pi times capital R squared. Again, that's the area where the magnetic field is confined to. And then we could even write cosine of 0 degrees because, again, the area vector and the magnetic field are parallel to each other. Once again, the only thing that changes is the magnetic field, so we can take these out of the derivative and and also the pi goes away. So the electric field, when we solve, is, all right, so, okay, let me make some room. So let me create a pause to give you a moment to copy these notes down if you need a little more time. The last thing that I want to do is plot the electric field for all the regions. As you know, very common in a physics problem to show, graphical representation of what's going on with the electric field. So I will create axis of electric field and radius. Now the formula I erased, unfortunately, was E equals R over 2 times dB dt. Okay, so that's the formula for the electric field inside the solenoid at 0 at the middle of the solenoid, and then it grows the further you go out from the solenoid, reaches some maximum value where we switch to that formula, which, as you can see, is a 1 over r graph. So that means at twice the radius, we've got to have half the electric field. Well, I don't know how good of a curve that is, so I'll fix that up by writing what the proportionality is. Same with here, proportional to r. The maximum value, I can either plug in capital R into this formula or into that formula over there. Easier over here. And we could say R over 2 dB dt is the electric field for all parts of the solenoid, both inside the solenoid and outside the solenoid. There it is. So let me create a pause to give you a moment to copy those notes down. Okay, so that concludes today's notes. Again, a very profound and beautiful rule that a changing magnetic field creates an electric field. Electromagnetism linking together. There's more to the puzzle about the linking of electric and magnetic fields, but you're going to have to be patient. for a few more videos when you see the full, complete picture, and I promise it'll be worth it. So I hope you enjoyed today's video. I hope you enjoyed the physics, the demonstrations. Don't try the coil at home and get electrocuted. Please, please don't do that. And I'll see you in the next physics video.